tady vlastně po tobě, ani nevím.
Po mně je potopa.
Že by... tady.
Sef radost, no výborné.
Korit 8 a korit 8.
Jo,
to nemám páru.
To je dobré, to je sef a to je Glaster. A to je taky Glaster.
NFS Ganesha a Glaster.
No jasné, a to na tím je taky Glaster, to je Ultimate.
To je taky blbý, že to neviděli jako nějak.
Jasné.
Přijdou samý známý, ne? Jinak se tam dá tady nastavit, že jo? Když si nastavíš ten čas, tak to zavibruje za určitou dobu.
Také uspokojení nepotřebuje.
Co tady už tím, co měl? Tady měl jeden francouz, to taky tady, francouzská angličtina na svou. Ale to
Ještě si sundám hodinky. To já už nevím, jak po někom hodím tady to místo té šály. Thanks for the question!
Jinak buď jim to můžeš hodit rovnou, což si myslím, že ty budeš dělat rád. Ale nebo oni si můžou popřed akci.
To nevím, jak je to těžké. To bych chtěl tu flašku do toho tam valit.
Házel to tam do třetí řady nebo do čtvrté.
Okay, shall we start? So, hello everybody. My name is Vratislav Podzimek, and I'm the member of the storage sub-team of the Anaconda installer team. And my topic for today is finding storage Neverland. I think it's kind of an abstract topic, and it may be hard to imagine what goes into that topic. But to give you a little bit of introduction, when I started to work on storage in the Anaconda installer, I was really confused with all the letters, shortcuts, and various names that didn't make sense to me. And it was really hard for me to somehow orientate myself in all these things. And when I finally figured out what these shortcuts and words mean, I must say I was kind of disappointed how hard it is to work with these technologies from your programs and applications. I knew many tools from Bash and using the command line tools, but I always thought that when I start programming and trying to do something with storage technologies, I will have some libraries and APIs available that would help me to do so. And so it was kind of hard for me to somehow stand in the storage land. And so I started dreaming about some storage Neverland. And I'm sure we'll reach that point at some time, and we will be living in the storage Neverland. So my goal today is to present the storage land to you and to present the difference between the storage land and storage Neverland. So first of all, as I'm going to talk about storage, this is my little introduction to storage as I see it. It's totally simplified, and if you feel like something has to be added there, feel free to talk, and I can even repeat it to the mic. So this is how I see storage. We have something like 3 layers, where the first one is disks, plus what I call the enterprise storage. If you have a better name, then speak. So as for disks, we have HDDs, which are still the most widely used technology. Then we have SSDs that are kind of slowly replacing HDDs, but not particularly replacing. They are complementing HDDs. And so there are some solutions that use both HDDs and SSDs in a combination to make best of both of these technologies. So basically to get a speed of SSDs and a capacity of HDDs. But then we also have SMR, which is shingled magnetic recording, which are basically HDDs, but with a crazy capacity. And then we have some old dinosaurs like DASD, which is the IBM mainframe disk or disk device technology or disk-like technology. And most recently we have NVDIMM, which are non-volatile memory disks, which are super fast, super expensive, and super promising. And we will see what gets from there. So these are what I call disks, even though they are not disks in particular. And then we have something like enterprise storage technologies, which is, for example, iSCSI, which is basically transporting the SCSI protocol over Ethernet or Internet or whatever. Then we have ZFCP, or I should start with FC and FCOE, which is fiber channel and fiber channel over Ethernet. And ZFCP is the IBM System Z implementation of the fiber channel protocol. And then, of course, there for a long time there has been SAS disks, which are just like normal disks, but they provide some nice features and, as I understand it, a little bit more information than traditional SCSI disks. So this is the first layer, and then we have the block devices layer, where we build something on top of these disks that can be better used by user and also by what follows, which is formats. We have partitions, which is the basic technology, but still most widely used as far as I can tell. So these are MBR, the master boot record, and GPT tables, which create partitions. Then we have MD, which is multiple device, which is a kernel driver. I'm not sure if it's a driver, but it lives in kernel, and in most cases it takes care about software rate. Then we of course have loop devices, which are most often used for testing. They are not used in any serious storage configuration, as far as I can tell, unless you are using Docker in its crazy early versions and years. And then we have device mapper and LVM and LUX. These three are closely related because LVM and LUX both use device mapper. Device mapper is in kernel and user space, and it takes care about abstraction of storage, and you can do many crazy things you couldn't even dream of. So if you have some extra time, definitely take a look at device mapper and LVM and their new features, which are being added every month, or definitely between two DEF CONF conferences you can definitely find something new in LVM and device mapper, so don't forget about that. And then on top of the block devices we have formats, which are usually file systems, but for example also SWAP, which is not a file system, but it is a format that exists on a block device. Also, I kept Ceph and GlusterFS outside of the file system because I don't consider them traditional file systems. So if you look at it, it's kind of easy. You have disks, and then these disks are transformed into block devices or provide block devices. And those block devices are used by formats. But it's not that easy, because, for example, you can take a disk and provide it over an iSCSI as something that is basically a disk, but on a different computer. Also, you can take a block device created, for example, by LVM, the LVM LV, and provide it as a disk over iSCSI for a different computer. You can take a block device and create another block device on top of that for example, you can have MD-RAID, and on top of that, LVM and LUX, and whatever you want. You also can have a file system that exports another file system. So, for example, GlusterFS uses XFS, but multiple XFS file systems, and exports them as a single file system. And most recently, what I found yesterday is that those new file systems, Ceph, Gluster, and probably something else, are also working on support to providing block devices. So it's really kind of crazy. And then finally, there is this question mark. Any idea what is missing in this picture and what should go into instead of that question mark?
ButterFS?
Yes, exactly. ButterFS, the endless source of ifs, special treatments, and everything in code, which combines block device and format or file system technology into a single package.
So, where would you put something like NFS first of all, or GFS?
NFS is a file system, and GFS is also a file system.
Yeah. So, but then why didn't you put Ceph?
Well, I consider NFS and GFS as a file system, where these two are like kind of a different technology. It doesn't matter. It's not a complete picture. There are many things missing. For example, I should have mentioned something like DM-RAID, which is slowly being replaced with MD-RAID and in another direction. Whatever. So this is the simple view of how things go in storage. But as we are on the developer conference, here I come with something that I call a developer's view. And this is how storage works from the developer's point of view. At the very bottom layer, there is kernel, and the code that is implemented in the kernel, which is file systems. Then kernel takes care about partitions. The MD code, DM code is in kernel. ButterFS, of course. Yes.
It's not special, to be honest, and I don't like when people say that ButterFS is special. It kind of isn't. It's the same file system as any other, but it has some special features, that is true.
Yeah, it's a file system that spans across multiple block devices. Which
Right,
is,
that's not something.
yeah,
It's still just create different volumes, but it's not.
I
It doesn't create any block device.
Right.
Just use block device.
yeah.
I just don't want to have to give away the information that to people that it is something different than a file system, because it's definitely a file system.
Yes.
It's not anything else.
But what I mean in this slide is that, or especially in the previous slide, is that it's kind of quite a lot of code put into kernel, which takes care about things that are usually handled in a separate code, like replication data and things like that. I don't know. ButterFS is a topic for multiple talks. You can have one. I think it will be very interesting. And then you have the loop device support and iSCSI and many others. So this is the kernel layer. And then there is the low-level user space, which is the tools, libraries, and utilities that communicate with this layer. Usually it's via the IO calls to kernel, or writing data exactly to some specific places and triggering kernel to read them and process that. So these are all the MKFS tools. It is also the lib packet library, MDAEM, LVM, DM setup, which is using libdevmapper, which Kabi was talking about at the previous talk. Also multipath, crypt setup and the libcrypt setup, ButterFS procs, LO setup, and iSCSI tools. I picked iSCSI ADM, but there are multiple of them. And libiSCSI. I will get to libiSCSI later, and you will find out why it is here, and it will be. I hope it will be kind of funny and interesting for you. So these are the low-level user space tools and libraries which give you the biggest control over what you can do outside of doing the kernel calls. Usually, you can do everything the technology supports in low-level user space. I don't know about any example where you could do something with, for example, I don't know, device mapper that wasn't exported outside of kernel in a different form than IO2 calls. So it's usually all, or as far as I can tell, it's all available in libdev mapper and VM setup. So if you are writing an application and, for example, web interface, you don't want to do IO2 calls to kernel, but you usually don't want to use these tools and libraries as well because they are really complex. They provide you with great power, but you have to take care about many things. And if you don't want to guess values, you have to ask user for values that they have no idea what these mean. I don't know, for example, many people know LVM, but if you ask what the extent size for their VG should be, then many people struggle. They have no idea what an extent size is. They want to use LVM, but they don't want you to ask them for that value. And even though you don't have to pass it to LVM, it has some default. It's not the case with some other values that you have to pass to this layer. So then there is what I call the APIs layer, which are a little bit higher than the low-level user space, and they provide you with some nicer API that is usually smaller. You lose some functionality. You cannot control everything like you can in this low-level user space layer, but it's usually much easier to use and much nicer to use. And in this layer we have libblogdev. I will get to that later. It's a library for manipulating block devices in general. LVM dubstep, which is a proof of concept implementation of LVM dbus API. Multipath dbus, which is the same for multipath. And also targetd, which is a daemon that you can interact with to export, for example, iSCSI devices from a server, and you can then work with them on your client, if I call them with these names. So this is the low-level API, which gives you a lot of possibilities, but it's still kind of close to the low-level user space. It's an abstraction to some extent, but it has no extra abstraction that you could like to use in your high-level tools or even libraries and whatever. So then there is storaged and blivet, which are, well, many people don't understand the difference between storaged and blivet. I will also get to that later, but the basic difference is that storaged is allows you to do things in step-by-step way. So every change you do, you commit it to disk and then go on. Whereas blivet allows you to change the in-memory model of your storage configuration and then commit it to disk in a single step. So it's kind of a transaction-like model, but it's not a transaction at all. You cannot roll back. You cannot do things like you can do with real transactions, for example, in databases. But it is an abstraction to the extent that you do things and then commit them in a single step. And then there is the storage management, which is a library that allows you to work with various SAN related things in a vendor agnostic way. While the interaction between these two layers happened with IO2 calls, usually between these layers you have either a C or Python API, or you are calling CLI tools, which is really suboptimal because forks are, for example, eating random data entropy, which doesn't probably bug you when you are working on your system, but it's kind of a problem in the installation or it could be a problem in the installation because there are limited resources resources of random data entropy. And if you do a lot of forks, then they eat your entropy, and it is gone when you, for example, needed to create, I don't know, SSH keys for your server or encrypting your disks. So we are trying to, so the discussion is about to minimizing the CLI interface between these two layers. And then there is the user interaction layer, which is, for example, the Anaconda installer. I intentionally put parted here because it's a command line tool that provides, I would say, a high-level approach to creating partitions. And there's also Blivet GUI, which is a graphical user interface on top of Blivet. So you can think about it as gparted with some extra functionalities. It can work with LVM, it can work with Btrfs, MD-RAID, and things like that, because Blivet supports all of this, and it does it in this modal change commit way. And there is SSM, the author of which is sitting right here, which is a nice tool that provides a nice abstraction on top of these block device technologies, and in a unified way. So, for example, you can do a snapshot of LV, and you can do a snapshot of Btrfs volume. But as a user, you don't want to care about if it's LVM or Btrfs. You want to create a snapshot. So you can use SSM and tell it to create me a snapshot of /home. And it just creates that snapshot. And you don't have to care about the underlying technologies and things like that. And it has many more such features as creating volumes and things like that. God. Yeah. And so from the web technologies, there is Cluster Management Console, Calamari, and you probably know Cockpit, which is providing a web user interface to server management or workstation management, but it includes a lot of functionality related to storage. And then Unified Storage Management or Manager, whatever the name is this week, it's basically a unification of Cluster Management Console and Calamari. So something to manage Gluster and Ceph together. I think the next two talks are about Ceph, Gluster, and then Gluster again. So you can ask these guys. Okay, so we have these layers, and it's obvious that, for example, StorageD uses LVM to set up LVM. SSM uses LVM to do things. SSM uses Btrfs and things like that. So it sounds nice, but the reality is not that nice. The reality is this. And you may remember the funny picture who sues who with the patent trolls and all those patents, which company sues which company for patents. So this is kind of a similar picture, because if you take, for example, Blivet, it is used by Anaconda and Blivet GUI. So far, so good. It uses libblockdev. It also uses StorageD. It also uses MKFS utilities. It also uses libparted. And if you go through the transitions, for example, StorageD uses libblockdev and things like that, it's really hard to somehow take sense from all of this. And you can believe me that another like 50 arrows are missing in this image.
Did you draw them?
Sorry?
Did you draw them, the
Yeah.
arrows?
Yeah.
How long did it take?
It was actually kind of easy. There are not so many of them. So you can probably take the most important fact from that, and that is that this is really a mess. And so this is the storage land we have right now. And as you can imagine, in the storage Neverland, where I hope we will somehow at some point get, there will be a lot less errors. All the arrows would be going in the single direction from bottom to top. And there wouldn't be crossing so much. So for example, if something is implemented in storage D and something from the upper layer wants to use it or wants to do something with, okay, let me rephrase it in a different way. No arrow or as little number of arrows should go over a layer. So for example, if SSM wants to do something with LVM that is already implemented in storage D, it should simply use storage D. It shouldn't bypass it. If the API is not ideal for SSM or Blivet or whatever, the API should be extended or there should be some extra features added to storage D. Because in this way, we are duplicating efforts and we are duplicating a lot of code. And most importantly, we are duplicating a lot of bugs. Because in some cases, LVM, for example, asks you for confirmation because it is a CLI tool and it expects a user to be sitting on the other end. And so we have a code in SSM that makes sure that LVM doesn't ask, and if it asks, to give it an answer. We have the very same code in Blivet. We have the very same code in storage D. And we are, every piece of that code has its own bugs. So
I just want to propose that the solution would be to have a LVM library and
yeah, I will get to that later.
That'll be great.
Yeah, that is the great goal. So I think, and of course, if you think about networking and network stack, they have maybe not so many technologies, maybe less layers in this area, but they would have a big round circle here that would say network manager. And there will be a single daemon taking care of basically everything that can happen in networking. So the question is something like a network manager of storage a good way to go? And yeah, I see many people shaking their heads. I have seen a lot more people shaking their heads on their question. It's probably not a good idea because there are really many technologies and it would be kind of a bottleneck and many people have problems with network manager. For example, it's still not running in the early boot phase in the Drakehood because it has a lot of dependencies. It's kind of slow for some use cases and things like that. So we probably don't want to do that. But if you think about it, the situation is not that bad. The only thing I really hate is this arrow going in the other direction, which is storage D using parted. Peter is here. Yeah, he's sitting over there. So I always thought that storage D uses lib parted. But I think, if I got it right yesterday when I checked, it's using the parted utility, which is kind of pointless, and I hope a bug filed will be fixed. So we need to get rid of many of these arrows and do things in nicer ways. But since we are on a developer conference, I would like to focus on those APIs and maybe help you guys or your friends and whoever you can talk to not add more arrows here. So let's focus on the APIs. First of all, which are the most recent two things that are currently being developed are LVM dubstep, which is a LVM dbus API prototype, and multipath dbus, which is it is a read-only dbus API for multipath, so you cannot do changes to your multipath configuration, but you hardly ever do that anyway. So the read-only API is kind of enough. The LVM dubstep is a replacement for lit LVM, and the replacement uses these double quotes on purpose because lit LVM is really a fail, and it started to exist. It provides a very limited functionality, and it seems to be a dead end. And there are many reasons for that. I hoped Kabi to mention that in the previous talk, but the biggest issue is that LVM needs to lock itself in memory, because if it ended up on a swap, then the code that should activate the swap back could be on that swap, so you would end up with a useless system. So it's a greatly simplified view, but there is a reason for that. So it is a replacement in double quotes because it surpasses libLVM to a great extent. It provides much more functionality in a much better and nicer way. It is right now it is implemented in Python, but this week I heard a promise from the LVM team that they are going to rewrite it into C at some point and take it under their wings and develop it. Because right now it's developed by Tony Asleson, who is not member of the LVM team, right?
Not the direct one. He's going to other UVs in the future or something.
Yeah.
So that's why he's requesting that.
I know.
One, right?
Yeah, I know.
There's technical reasons as well.
Yeah, sure. So right now it's in Python. It doesn't matter too much because it's really faster than most of the use cases really need. So it's not a big problem. As I mentioned, it is actively developed, extended, and improved. It also provides events and signals for changes happening in LVM, which otherwise are kind of hard to gather from UDEF events and things you can monitor. And so the ultimate goal is to provide a version-controlled, non-forking, non-blocking interface to LVM. Very similar situation with multipath, except that it was kind of funny that originally there were two versions because two people had the same idea and chose a different approach. One of them wanted to add a thread to multipath D, and the other was using clip multipath. And the second approach seems to be the better one because the multipath D people are really not fans of adding new threads running in their code and things like that. The other two APIs are the liblogdev, which is a C library. The first goal was to rewrite Blivet's backend that was written in Python to C, so that it could be used by other projects as well. It provides support for Btrfs, LUKS, DM, something that I call kernel block devices, which is ZRAM and Bcache, loop devices, LVM, MD, MTAP, and SWAP, and S390 storage, so those DASDs and things like that. And it is a stateless and synchronous library, so if you ask it to create an LV with in a non-existing VG, it fails to do so just when it calls LVM and returns the result. It has no state, it doesn't remember that a VG was created or things like that. And there is a very tiny library called libbitesize, which is just a combination of GObject and GMP, the GNU multi-precision library, which allows working with big sizes over the max uint 64 bytes, and it provides unified human readable representation of sizes. Yeah, so these two are more for information about the enterprise storage. I'm not sure how much people are interested in about them, so I think I can skip them. If you want to ask something about them, then reach me later. And these are the three main high-level APIs to kind of APIs. StorageD is a successor of UDisks2. It is the UDisks2. It is basically the UDisks2 codebase that was made modular, and it adds some enterprise technologies like LVM, which is the default storage configuration for Fedora. So I'm not sure how much that is enterprise technology, but it was for a long time rejected by the UDisks2 developers, and it resulted in in creating a fork of udisks2 and calling it storage-d, because now we can add this functionality that we need. It provides low-level API for block devices. As I already mentioned, it provides the step-by-step approach, and it provides both passive and active functionality. By passive, I mean that you can get information about block devices from there. By active, I mean that you can actually change the block devices. And also signals and monitoring. I already mentioned something about Blivet. It's written in Python. It's used by the Anaconda installer. It provides a high-level API, uses libblockdev and storage-d, as you have seen in the arrows. And very interesting thing about it is that it also, apart from the model and commit approach, it also provides device factories. So you can, for example, tell it, okay, scan my storage configuration and now create an MD RAID level 10 as big as you can on my system. And it takes care about everything else. It just goes on, then you can check what it created, and then you can commit to disk or not. And I already mentioned SSM, which, as far as I can tell, it has no real API, right? It's a CLI tool.
Exactly, yeah.
It's written in Python. You can import the Python module it uses, but it has no real nice API which would allow you to use the unified abstraction functionality.
I just want to see the reason behind that is that it was not designed to have a real API just because of the abstractions we made.
Yeah.
So that was the main reason.
Yeah, and it has been mentioned many times in the last few months that maybe the SSM approach is something that would fit into that network manager of storage, where we could provide some high-level abstraction and functionality to allow some developers as well as users do some high-level things, not caring about the underlying technologies. So these were the APIs you could use. And now I have a few funny stories that happened I would like to share. Here comes the liblvm. I already mentioned something of that. It was always wanted, as long as I know, as I have been in Red Hat for 5 years, everybody was talking about liblvm 5 years ago. And it turned out to be a dead end. And you know what? I'm kind of happy that it happened. Because now that everybody agreed it is a dead end, there are no more requests to create it in a way that many people always wanted to exist. And with LVM dubstep, the LVM dbus prototype, nothing is really blocking us from creating liblvm that would use the dbus interface. So it could be a C library with the dbus interface behind it back, and you wouldn't have to care about that. Also, another interesting thing was that I'm the author of the liblogdev and its Btrfs plugin, and I was requested to use the ioctl calls like the Btrfs procs do in my plugin, and I was like, okay, but then Btrfs procs should use liblogdev Btrfs. Because we only want to have the code doing the ioctls in a single place. So why not make Btrfs procs use? And of course the Btrfs people were like, oh no, that's not gonna happen. I was like, okay, so then come up with libbtrfs, and we can call that library both, which is the way to go. libiSCSI is a very funny thing, because actually this is libiSCSI, which is a downstream patch for open iSCSI sources, and it is shipped as part of the iSCSI initiator utils package we have in Fedora. But the original upstream tarball only provides a command line utility, and we have a patch that creates a library from that command line utility. And the code in that command line utility is really not written to be aware of any other code running in the same process space. So, for example, if you call some function from this library, it can freeze your process for 12 minutes, because that's what the command line utility does, and it has no things for that. I already mentioned LVM CLI usage. We have more than 4 implementations of parsing out the output of the LVM CLI. And as the LVM team, I think it was last year, they presented something they call the -- select option. I internally call it LVM SQL because that's kind of what it allows you to do. It allows you to cherry pick information, the very little piece of information that you actually need, and then you don't have to parse it. Except that we started doing that, and we now have an open bug that Blivet is scanning disks for 12 minutes and calling LVM CLI 800 times by doing that. So we are cherry picking the information, but we are cherry picking it in 2,000 instances. So these are kind of sad stories. The nicer stories are libblockdev using LVM dbus now. And there are 2 plugins for libblockdev, both providing the LVM functionality. One is using the CLI, one is using dbus. The dbus, of course, provides significant speed up and less forks, and is completely transparent to the caller of libblockdev. So if you use libblockdev, like Blivet does, you don't have to care about if the LVM dbus is available or not. It will just work and use the better option. And also one nice story, Blivet is using storage-D iSCSI now, because we used to have a code in Blivet that was doing iSCSI operations, and we didn't like it. So it was removed, but actually moved to storage-D. And we now have this, at least we now have this ugly code in a single place. So we are deduplicating code. Okay, I'm out of time. So thank you for your attention. You can reach me via email or on IRC, or here. I will be here tomorrow. So if you have any more questions or things like that, feel free to catch me.
Thank you for the great presentation. And if someone of you wants to travel to the party today, please there are a few silver tickets on the recreational equipment
Presentation, please.
Yes.
So given that, do you still think there should be less individual projects developing stuff like this?
Yeah, I believe there should be less projects.
But wouldn't it be the same argument as having less distributions? To just have 3 major distributions and they'll fix everything because each distribution re-implements what the other distribution did?
Yeah, but it's kind of pointless to, for example, have a code that parses output of LVM.
So,
Like
I mostly agree
places.
with what you say, but it's never going to happen. It's never going to reach a point where you have just a couple of projects doing the exact same thing. So, let me talk to you with that. I'm Alex. I'll be introducing you. So, let's get output.
He's the one in the red sweater, I think. Ah, he's right here. Let's say, Samantha, where are you?
Co jsem chtěl zeptat, vy teda používáte ten LVM dbus věc?
Já jsem teďka dělal ten libblockdev plugin, který to používá.
Jaký je ten rozdíl proti volání, jako myslím, použitelnosti a rychlosti? Protože na pozadí to stejně pořád dělá to tež, ne? Nebo...
No jasné, ale minimálně to dělá to, že ti to třeba LV snížíš a tak dále, se natáhne kdyby jednou.
Interesting that it didn't detect from the start.
Jo, ale zároveň poslouchá na UDEVu a updateuje to a tak dále.
Je takhle, takže to můžeme proto si to vidět.
Chcete šály? Chceš šály? No,
jsme se stanovím a přepis LVM dubstep do C je dost pravděpodobný.
Aha, no tak nevadí. Já pracuji s informace.
Tisíce řádků kódu v Pythonu.
Tak to jsme říkali od začátku.
Budeš mít chvilku čas potom?
I think it's better to just move the presentation to the screen so you keep your laptop too. You can put this in.